Boom. Hello and welcome back to Calculus 1. We are starting Chapter 3. Chapter 3 is on derivatives. And the first lecture is the lecture to define the derivative and see how to calculate the derivative in the worst possible way, and that is using the derivative from using the limits from Chapter 2. So I'm going to start by making sure you know that derivatives measure change. Derivatives measure change. I'm not sure if you're familiar with the fact that you are the tallest for the day when you get up in the morning. Like in the morning, you are the tallest because while you were unconscious, you stretched and your joints stretched. So when you get up in the morning, you are tallest for that day. As you drag your weight throughout the day, those joints slightly compress in your ankles, knees, hips, everywhere, and you are fraction of an inch, not noticeable, right, by our eyes, you are shorter. The same goes with your weight. You are lightest when you wake up in the morning because your body used up a lot of energy, whether you had food or the supplies, throughout the night to keep you alive. It takes a lot of energy to run your internal organs. Your brain to generate electricity, which needs to be distributed through the bodies, the small electrical impulses through the synapses of 14 nanovolts or millivolts, can't remember, is the one that makes your muscles twitch, which makes the heart twitch, which is the pump for the blood that distributes oxygen and so on, right? A lot of energy goes into converting all of that and just staying alive. You are actually burning considerable amount of energy just by sitting on a couch and doing nothing. Obviously, you use much more if you are on a treadmill. So, you are the lightest for the day when you wake up in the morning, and then your weight throughout the day will go up as you eat along the day. When you drive your cars, you are constantly, as a system, lighter and lighter and lighter as the fuel in the tank is being used up and converted into energy and heat and friction and all of the other things. So the car, as you are moving, is constantly lighter. All of these constitute change. Change in mass, change in length, change in something, and we measure that with derivatives. Now, we also know that in algebra, we measure change by using the slope of the linear line. So this is where our story begins. It's actually 2.1. We draw a line, a linear line, and we learn about its slope. And then we upgrade that to the concept that we need in 3.1, opening the door to calculus. So here we go. We have some kind of a function. We call that f of x on the xy axis. We are, yes?
So conceptually, like a limit will give you a direction of change, whereas a derivative will give you the amount of change.
the amount of change is correct. The limit is completely used differently, so we'll see that. But keep the other one. I'm going to pick 2 points and connect them with a straight line. This straight line is called the secant line, and the secant line is actually secant line, and that's actually your algebra line that you know from y equal mx plus b, that you all know and love. Now, I'm going to say this is point P, and I'll say this is a fixed point, and this is a point Q, which I'm going to allow to move this way. Now, my fixed point P has value A because that's fixed, and my point Q has value X, and it is here where you see that X is gonna go to A. I understand that you are used to writing X goes to A this way, but for the purposes of this picture, X goes to A, so X is gonna move to the left. As X moves to the left, point Q is going to obtain different location every time it moves, creating new secant lines. Every time you have a secant line, its slope will simply be y2 minus y1 over x2 minus x1, which is your standard algebra formula for the slope. We call this m secant with SEC, right? That is a slope of the secant line. In pre-calculus, you learned that y is equal to f of x, and I can plug that in, creating slope of the secant line is equal to f of x2 minus f of x1 divided by x2 minus x1. But when I look at my picture, I realize that point P has coordinates A, f of A. And I realize that point Q has points X, f of X. Because if A is the input, output better be f of A. And if X is the input, output Y better be f of X. So now I'm going to plug in these into my secant slope formula. So now m secant becomes f of x minus f of a divided by x minus a. And I am going to box this formula, and I will write word algebra, because I haven't done any calculus here. I just renamed the good old algebra formula into what we have through pre-calculus language. So your point x2, y2, which is point P, x2, y2 has f of x and x, and your point x1, y1, which is your point P, has a and f of a. So y2 minus y1, x2 minus x1, written in the language of pre-calculus to match the picture we have. No motion. All what you see over here is 2.1. That's 2.1. Setting up the stage for motion to begin. Where is the motion? Point Q is going to move to the left towards P. Every time it gets to a different position, it is going to generate different value for the slope. Each blue line is the new black line. We call that secant line, which means to cut. And you see that obviously as Q changes, coordinates of the Q change, which creates different value for the slope. All of the blue lines and the black line have a different slope because one point is fixed and the other one is free to move, creating infinitely many slopes there. Now, algebra is happy to compute all of these slopes. As soon as you know the coordinates of point P and the location of point Q, you can run your algebra, basic algebra formula to calculate the slope of the line like that, which calculates the average change in price or weight or whatever you are trying to observe. So we are all good with algebra. There is the one instance where algebra fails. What is that instance? Yes? It still works. When it's really, really close, it still works. When is the problem?
The denominator.
When does that happen? It doesn't happen when it's very close. It happens when it's... No. Not when it's further away, not when it's close, not when it's very close. When it's exactly there. Exactly. Okay. So, you were close. So, point Q is going to approach point P. No matter how close or how far they are, algebra will be able to calculate the slope of the secant line. Hell breaks loose as soon as point Q collides with point P and they are at the same location. When point P and point Q are at the same location, their x coordinate is the same, making x minus a 0, and your algebra stops working at that instant. No more algebra because you are dividing by 0. So, do we still have the line there? The answer is yes. All these blue lines point that there should be some kind of a red line there, like that, and then the Q will pass on the other side of P, creating again blue lines, which you can take care of with algebra. So the only time when you cannot run algebra to do this calculation is when Q collides with P, which creates the denominator to be 0, as you noted, right? So what do? Is there a concept that would help us compute the slope of the red line since algebra failed? Now you go at this and you look and you say, I have infinitely many lines before, infinitely many lines after, I don't have this one. Which mathematical concept deals with those types of calculations? Limit. Remember that the limit never computes at the point of interest. Limit computes everywhere else, never at the point of interest. My point of interest is A. So, the limit is perfect for this. We will have all of the blue lines to the left, slopes, and all of the blue line slopes on the right. So we use the limit to calculate the slope of the red line, which is where algebra fails. So, the red line is called the tangent line at x equals a, and its slope is m tangent is equal to limit of m secant as x goes to a. So the red line is called the tangent line, and it's special. It's special. Each point on the function has exactly one tangent line. It's a very special line. So you are going to have infinitely many secant lines before and after tangent line. Tangent line is the one. You see in the matrix, right? You know what the one means. Who's the one in matrix?
Yeah.
Agent Smith, of course. Exactly. Look at the requirements to be the one. He has to be born in the matrix. Agent Smith is the program born in the matrix. Neo is a human born outside of the matrix. You remember the 3 rules of continuity? It fails the first rule. Neo is not the one. Agent Smith is. Plus, when you see the end of the movie in a third movie, you also see something between Neo and Agent Smith. So that's another clue. Anyway, it's so interesting to see that pretty much everyone gets the movie wrong. I love it. But I love Keanu Reeves. Still irrelevant. All right. Now, I'm going to replace m secant with the formula that m secant is. So, m tangent is equal to the limit x goes to a of f of x minus f of a divided by x minus a, and I am going to box this 15,000 times with all different colors and things that I have. Let's put the orange barbed wire on it. Gotta protect this, you know. There we go. Now, depending on how much time you have, you can go and make those barbed wire things, you know. I'll leave it there. So this is the slope of the tangent line. And this is really powerful stuff, guys. You were always taught that in order to find the slope of the line, you have to have 2 points, x1, y1, x2, y2. Tangent line happens at the single point. Please take some time to appreciate that. You will be able to find the slope knowing only 1 point. Wow. I mean, if that is not amazing to you, you have no emotion. So let's find the tangent line. Find the tangent line. Guys, it's going to be TL, because from this point on, tangent line problem becomes the central problem of Calculus 1. And we will be drowning in tangent lines in chapters 3 and 4. So TL for the rest of the course. Find the tangent line for f of x equals x squared minus 1 at x equals to, let's say, 3. All right. What I gather from this x equals to 3 is that a is 3, because you are looking for the tangent lines at x equals a. If you have x equals 3, then a is 3, which is x, which is making it very confusing, I know, but such is life. So 3 is the fixed point for that point P. If I plug all of this in my limit, I will get that the M tangent is equal to limit x goes to 3, because a is 3, of f of x minus f of 3 divided by x minus 3. I also know that f of x is x squared minus 1, and I can plug that in as well. So now this becomes limit x goes to 3, f of x is x squared minus 1 minus f of 3, well, that's 3 squared minus 1 divided by x minus 3. So when we go through the layers of chapter 3, you are now faced with a basic limit from 2.3, right? And you just have to solve this. So what do I have? Well, simplify to see what you have. You have x squared minus 1 minus 8 divided by x minus 3. You have limit x goes to 3 of x squared minus 9 over x minus 3. And how do we solve this? Factor. Limit x goes to 3, x minus 3, x plus 3, divided by x minus 3. This dies. We are left with the limit x goes to 3 of x plus 3, which is 6. Slope of the tangent line at x equals 3 is 6. Now I am going to write this in blood. Mechanics of this calculation are in 2.3. So this is why I said your concepts are chapter 3, your calculations are chapter 2. You have to take the limit. That's chapter 2. Well, great. We have the slope of the tangent line. What does that mean? That means that if I am to graph this, we have x squared minus 1 This is a terrible graph. If you go to 3, there will be a tangent line at 3. Whose slope is 6. Yes?
Is there ever a situation where you would not be able to factor that out?
Of course. We are going to have square roots, and we're going to have 1 over x, which is the next example.
Okay.
So the solution of this solely depends on your skills for 2.3, which are all different types of limits that you factor, cancel, rationalize. Whatever magic you have to or learned in 2.3 will be applied. We are not learning any new methods of calculating things. We're going to apply all of 2.3 to solve without adding anything new.
Okay.
So what's new in 3.1 is the concept of what that means. Calculations are 100% what you learned in 2.3 and nothing more. Yes?
So, put this another way, is it like taking the slope of the, not the limit of the slope equation? Is that what we're doing here?
Yes.
Okay.
We took the limit of all secant slopes.
Okay.
And we got a tangent slope. Fair? All right. Now, how about we still have the same function, x squared minus 1, but we actually want to find the tangent line at x equals to 5. Yeah, we have to start from scratch. So, limit, x goes to 5 now, and we have x squared minus 1 minus 5 squared minus 1 over x minus 5. So now we have the limit, x goes to 5. We have our x squared minus 1 minus 24 over x minus 5, which is limit x goes to 5 of x squared minus 25 over x minus 5. Again, factor cancel. X minus 5, x plus 5 over x minus 5. And we get 10. So the tangent slope is 10 at x equals to 5. You know what? I didn't really want a 5. I wanted -7. So same function, -7. -7 is better, you know, for everyone concerned. Well, from scratch, limit x goes to -7 of x squared minus 1 minus negative 7 squared minus 1 over x plus 7 this time, right? X minus a, minus a minus gives you plus. So this is limit x goes to negative 7. On the top I have x squared minus 1 minus negative 7 squared 49, so minus 48 divided by x plus 7, which gives me the limit x goes to negative 7 of x squared minus 49 over x plus 7. Hey, we can still cancel. So limit f goes to negative 7, x minus 7, x plus 7 divided by x plus 7. Kill. And the answer is, well, we have limit x goes to negative 7 of x minus 7, which is negative 14. So the slope of the tangent line is negative 14 at x equals negative 7. And then the boss shows up and says, I also need the slopes for 25, 31, right? Every time you have to restart the calculation, because every time you get a different a, you get different terms over here, and that ruins your day, right? So let's fix it. Let's make it easier to calculate, much easier to calculate. So now we do some mathematical gymnastics. We have our m tangent defined as the limit x goes to a as f of x minus f of a over x minus a. I'm going to define h as x minus a. And let's see where that takes me. So the first thing I can do, I see I can subtract a on both sides in the limit. So now I have that m tangent is equal to the limit x minus a goes to 0. And over here I have f of x minus f of a over what appears to be h in the denominator. Now, x minus a is also h. So m tangent is the limit h goes to 0. And over here I have over h, and now I want to, because if you take a look at this, guys, I eliminated all x's. There's only one x left. I can write that x if I flip this around. So flipping this will get me x equals a plus h. So I get f of a plus h minus f of a. This is a nice intermediate step. This formula still calculates slopes one at a time. Because you have A. Because we have A. And A is a specific point, specific location. What is the version that will allow you to compute all slopes at once? Well, when you replace those A's with X's. So it will make sense when I do examples and stuff. So now we are writing the final version of the formula. Limit h goes to 0 of f of x plus h minus f of x over h. This, put this on a cloud, this is the most important formula of 3.1 and the essence of the rest of the course. Does anyone recognize this? What is that? It has a name. And in pre-calculus you were told, calculate this. And difference quotient, nice. This part, f of x plus h minus f of x divided by h, is called difference quotient. You learned this in your pre-calculus 1 class. No one ever told you what it's for. You were just supposed to be annoyed by computing it. Calculate difference quotient for x squared. And you go, right? And you hate it because clearly it's useless garbage. Well, there it is. Difference quotient is the way to easily compute the slopes of the tangent line. Now, it might be still escaping you what is the point of the entire thing that we are talking about, but I'm going to remind you one more time. Any slanted line measures the change. You want to measure how much stuff changes. If I was this tall when I was a kid and I am this tall now, there is the time on the x-axis and the height on the y-axis, and there is your change. If I was 3'1" at one point in time, and I am 6'1" now, that's the difference of 3 feet over whatever amount of years it took. You have your slope of amount of feet per year as a change in height. I am able to measure my change in height as I go, right? And you observe the height changing. The time elapses as the x-coordinate, the height elapses as the y-coordinate, y2 minus y1, t2 minus t1, I have the slope. Now, that is the secant one. That is the one that it gives you the average. The question is, How much is my height changing this very moment, this split second, the infinitely small period of time where I am using the energy to run my body, when I am getting shorter because my weight is compressing my joints. To calculate that instantaneous change, we need this particular formula. Observe that age goes to 0. We are talking about infinitely small distance, infinitely small interval of time. This age goes to 0 is general. You get to plug in there the distance, the time, whatever your underlying base reality is, and then in respect to that, you measure change in money, change in height, change in weight, change in whatever. Make sense? So, this formula here measures those changes, and those changes are instantaneous. Another example that we are going to visit and revisit many times in chapter 3, as we talk about the difference between average and instantaneous, is going to be velocity. You see, to get from point A to point B, you are covering the distance in time. So if you want to know your average velocity, you will say, I went 60 miles in distance in 1 hour. Your average speed is 60 miles per hour. So what that calculation suggests is that you were always driving 60 miles per hour. Now dig deeper into that and think. Your car was hopefully parked in a driveway at the beginning of the trip. 60 miles per hour average means this. You either had ups and downs in speed, or you got into the car that was going 60 miles per hour, passing your house. You were 60 miles per hour through every stop sign, every red light. You did not stop for school buses or the pedestrians or the squirrel or deer. It was 60 miles per hour, and when you got to your destination, you roll out at 60 miles per hour and dismount, and voila, there you are, right? That's what the average thing tells you to do. You know reality is different because you are parked at your driveway at 0 miles per hour, and you push that gas pedal, and the car goes from 0 to 10 to 20 to 30 to 50 to 60, and now you are at 60. But if you are to drive 60, and let's say it's highway and no traffic and no lights and nothing, you lost those few seconds in the front. You will have to go somewhere over 60 to make it up, and you will have to brake for few seconds to make the full stop to exit the car. You will have to make up somewhere going over 60. When you are paying the speeding ticket, you are not paying for average speed. Cop doesn't know when you left, when you're gonna arrive, how far you went. Cop measured your instantaneous speed. This formula. Cop measured an insanely small interval of time using X-band or radar with laser. Laser travels at the speed of light. There you go. So, how small is the interval of time? Go use the speed of light and figure it out if the cop was 20 feet away from you when shot the laser there. So you pay the price for the current speed. Your speedometer in a car shows the current speed in time, the snapshot of every split, infinitely small interval of time, because you know as soon as you touch the gas, touch the pedal, the speed changes instantly. So this formula measures that. This formula is your speedometer. The secant formula is the average, and that is when you say, oh yeah, I live 10 miles away from RV and it takes me 20 minutes to get there. I divide those two numbers and I say your average speed is 30 miles per hour. All right, I know. Right, that's the part. So now, if you remember how to compute the difference quotient, the rest of calculations of this section will not be an issue. If you don't know how to compute difference quotient, well, you have still 7 days before you see it on the exam on next Saturday. Difference quotient is a formula from pre-calc 1. Calculating limit of the difference quotient is part of your homework in 2.3. I will have to go and find 2.3 problems now which prove that this is actually calculation in 2.3. There they are. They are in 60s. Old book, 60, 62, 63, 65. I will show them to you. They're there. There's more. That's just, those are the first ones I've seen. $46, $45. Also, all of these are problems which are difference quotient, which are in 2.3. As I said, mechanics 2.3, theory chapter 3. Okay. So, why is this formula powerful? Because the answer to this formula is not the slope, particular slope. Answer to this formula is a function. And now we're going to take a look at that. So, the next question says, find all tangent line slopes for f of x equal x squared minus 1. Same function as before. All right. Your difference quotient formula has a part f of x, which is where you're going to cut and paste what you have. But we also have f of x plus h, and that one you have to work out on the side. So, if f of x is x squared plus 1 and minus 1, then f of x plus h better be x plus h squared minus 1. Generally, when I teach pre-calculus, I say f of a heart is a heart squared minus 1. Whatever is in a parenthesis goes for that x. So, if the parenthesis changes x with x plus h, you better change your x with x plus h. leaving the rest of the formula the same. So every x will be replaced by x plus h, which involves now algebra and foiling and all of that stuff. Let's go. X squared plus 2xh middle term plus h squared minus 1. This is algebra foiled. Usually your grade withers as you forget the middle term over here, so try not to. When you are expanding binomial, the answer is a squared 2ab plus b squared. So there's the middle term, and that's this puppy right here. So make sure you don't mess that up. Let's go. Slope of the tangent line is limit h goes to 0. F of x plus h is this long expression, x squared plus 2xh plus h squared minus 1 minus f of x in parentheses divided by h. So all we did is we plugged everything in. Clean it up. X squared plus 2xh plus h squared minus 1 minus x squared plus 1 divided by h. X squared and negative x squared die. Negative 1 and positive 1 die. The only terms that remain after cancellation, and this goes for every problem, only terms that remain have h, which you can factor and then kill the denominator. So limit h goes to 0, factor out h, 2x plus h is left, divided by h, and now h cancels. You are left with the limit h goes to 0 of 2x plus h. What is your main variable in the eyes of the limit? Age. Age. In this problem, limit operates on age, not x, because its age goes to 0, not x goes to 0. There is the next pitfall of u. The variable that the limit is paying attention to is spelled out under the limit. So that means age goes to 0, so age goes to 0, x survives. No one is bothering x, so just copy it. In the eyes of the limit, that x is a constant, actually. We got 2x at the end. What was the tangent line when I had a to be 3? Look in your notes. I was 6. What was the tangent line when I had 5? 10. How about negative 7? 3 times 2, 6. 5 times 2, 10. Negative 7 times 2, negative 14. Is this always like this? No, I changed the function. That changes because you have to go to the calculation. Is it always the same for x squared? Yes. X cubed, it's different. X cubed is going to spit out 3x squared. Square root of x is going to spit out 1 over 2 root x. All right? 1 over x is going to spit out a negative 1 over x squared. Every time you change the function, the answer you get for the tangent line slopes is going to be different. The coolest of all, e to the x. Yes, very good.
At what point do we start to memorize this?
That's next class after the test.
Alright.
We'll start memorizing these things, yeah.
Yeah.
So at one point, I can tell you exactly that point. That point is exactly going to be 11 a.m. next Saturday. Alright? We'll be more precise when we get there, but 11 a.m. next Saturday is when you're going to start memorizing them. Alright, now we need to talk about this a little bit, right? Because we've seen this cool thing, and what I have over here is no longer specific slope. I have a function to generate any slope. And I made sure I screamed that word, any slope. So now, you give me x, I give you the slope like this. X equals 1, slope is 2. X equals a half, slope is 1. X equals 0, slope is 0. X equals 100, slope is 200. See how quickly you can come up with slope? You do not have to redo this calculation because someone gave you wrong number to begin with, right? So far, we have a lot of these things worked out. I started the lecture with a certain sentence. We ended here with, instead of computing individual slopes, let's compute a function that will generate every single slope that you want. This function has a name. And the name is the derivative. Very good. So what is the derivative? It's just a name. Okay, that's the derivative. So now we are going to write the essence. Sure, derivative measures change. Derivative blah, 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 blah. 2 chapters, derivative, derivative, derivative. What's this core essence of derivative? What does it do? Derivative is a function that generates all tangent line slopes. That's what it is. Derivative function generates all tangent slopes. And tangent slopes measure your change. So, as you are looking at your speed, you are looking at the values of tangent line, and the mechanism that gives you those numbers is the derivative. So I hope you see the connection between mathematical concept and something that you stare at every single day. Unless someone is giving you a ride or you're not paying attention, I don't know. but that's that. So when you go to the car after the class, you will look at it and say, oh, look at these tangent lines going from 0 to 200. Those are the slopes of the tangent lines. And when you are 85 and 55, paying 30 over ticket, right? You are paying for 30 tangent slopes over the tangent slope that was allowed on that road. Okay? So it's all tangent lines at that point in life. This is obviously excellent conversation starter for the dinner and dates and things like that. You can always start with, did you know? Right? And then you work it out on the napkin. Right? And obviously, as soon as someone says, what do you know? Let me show you. Right? And then you go work this out and say, so the tangent lines, right, are what you have on your speedometer, and, when you are 30 over, you are 30 values, 30 points of tangent lines over. So, at which point people will leave you alone and you can play video games in peace. I figured out life quickly. It's amazing. So, I can't scream this more than already am. This function is the derivative. It's just the name. All we used is 2.3 to get it. You did not learn today how to new method to calculate something. You learned that a certain calculation from your 2.3 now has a special name. And it's the building pillar of everything that we have as a species. Everything. So, the derivative is a function which computes all tangent line slopes. We say the derivative of f of x equals x squared minus 1 is f prime of x equals 2x. Notation. F prime of x, y prime, dy dx, ddx of f of x. These are the four that we are going to use in Calculus 1 and 2 and 3. First two are spin-offs of original Newton's notation, which was the y with a dot. People move that dot into a prime because you can have a second derivative with 2 dots and a third derivative with 3 dots, and then these dots become annoying, so we go y double prime, y triple prime, and so on. Much easier than dots conveniently placed above. Only certain mechanical engineers and older professors would be honoring the original notation of Newton. When I took course on statics and dynamics, when we did dynamics, my professor, this is 15 years ago, who at the time was in his 70s, was using the dot derivative notation. So you are going to run into it, especially if you go work at a company somewhere where the, head engineer in your department is older than fire. You know what I mean? Social security number, like 1. Yeah. I mean 0000001. That's what I meant. All right. Other notation that you are going to encounter as you go to different courses, different books, different math courses or engineering courses, which we are not going to use in class, but they exist, are y with a dot, original Newton's notation. You are going to see capital D of f of x in a linear algebra. That's called differential operator, which is actually this thing, just written as the capital D. You are going to see partial derivative notation when you put f with a subscript x, no parentheses. This is f of x. This is partial derivative of x. Subtle difference, right? Big difference in a concept. You will also see dx like this, and other notation that we really don't have to worry about. So this one and this one you're going to see in your linear algebra class if you go. This one you're going to see in Calculus 3. Oh, one more, Calculus 3. This is a partial derivative of a function in respect to x. It's still a derivative. All of these are notations for the derivative, and they all mean the same thing. So now, digging through this notation, I will say that f of x is equal to x squared minus 1, where f prime of x is equal to 2x. This is a full notation. Do not play with fire to write equal 2x, because it's not. This is parabola, this is linear line. They will never be equal. So do not play with fire. You go to the next line and you say the derivative is equal to, you are putting that prime there on f, and now we understand each other. Maybe you have notation as y equals x squared minus 1. Y prime is equal to 2x. Now, power of Leibniz notation. My favorite. You can say, what is the derivative in respect to x of x squared minus 1? And the answer is 2x. So, I told you here, don't play with fire to put equal to x, because you are saying function is equal to the derivative. No, no, no. Look over here. Derivative of a function is a derivative. Well, now that's okay as a notation. Do we all get the difference? Now, it's up to you. Do you want a two-liner or do you want a single line? You are allowed to do it. You can't mix and match. So, this line here says the derivative of this function is this. So great. Derivative equals derivative. Yay! Over here, a line for a function and a line for a derivative. Function is, derivative is. Derivative of this function is the derivative. So derivative equals derivative. So we're cool there. The derivative in respect to x of x cubed is going to be 3x squared. This is, after the test, you are going to learn shortcuts so that you don't have to crank that limit every time you need the derivative. And there will be 2 chapters of needing the derivative 15 times per problem. So, can you imagine doing 15 limits? Right? No, we want to X that out. So, now we practice more for the exam, right? If I want to ask this as a chapter 2 question, I just go and ask find the limit of a different quotient for a function. See that? As a chapter 3 question, I say find the derivative using limit. It's the same thing. It's just, you know, it's called loophole. I can ask chapter 3 question because calculation is 2.3. So I will say find the derivative of f of x 1 over x. Now this is technically problem 46 in your textbook, in a blue one, the old one, the one that it's on my MATLAB currently. Yeah, so 2.3 problem 46, and they also have that they want to compute this at 5 eventually, but I'm going to ignore that for now. All right, we know we need the difference quotient. That's f of x plus h minus f of x divided by h, and there's the limit as h goes to 0. Bueno? Emergency. So we have f of x is equal to 1 over x, and f of x plus h is 1 over x plus h. You replace x with x plus h. So now we need to plug this in, and we're done. So limit 1 over x plus h minus 1 over x, everything over h as h goes to 0. The only thing I can do is add fractions. I mean subtract fractions, right? So we'll do that, exactly that. Cross multiply. The denominator is going to be x times x plus h. Cross multiply on the top, so that's x minus h. Everything divided by h. Limit h goes to 0. X and x die over there. And we are left with negative h divided by x plus h over h. And if you want to make this easier for you, can put over 1. You have a double fraction to deal with now. It's all algebra. 1 times negative h is negative h, and on the denominator you have h, x plus h. So to deal with the double fraction, 2 that are far apart multiply on top, and 2 that are close by multiply on the bottom. That's the double fraction standard. So now h will cancel h, and you will have limit of negative 1 over x plus h as h goes to 0. Again, it is h that goes to 0. Do not bother x. Leave it alone. H goes to 0. So if h goes to 0, send h to 0, and you are left with negative 1 over x squared. So we say f of x equals 1 over x. F prime of x is negative 1 over x squared. The derivative is negative 1 over x squared. This is your answer. For the function input 1 over x, your derivative is negative 1 over x squared. And we use 2.3 to compute that. Yes?
So we're calculating limits here. Do you have to two-sided limits or can we work with one-sided limits?
Both.
Okay.
Yep. We can also write that the derivative of 1 over x is negative 1 over x squared. Right? That's another way to denote the same thing. Most of the time I use the one on the right because it's less effort, less writing, less mess, less lines, less paper, less everything. And to me, it's natural to say the derivative of 1 over x is negative 1 over x squared. You see that? It's just natural to talk that way, which is why I like this. Now, you guys still get full credit if you use this one. It's fine. So whatever makes you happy. One more time, the reason why I like Leibniz notation better is because I get to say the derivative of 1 over x is negative 1 over x squared. I get to say that in one sentence, and I get to write it in one mathematical sentence, which is one equation in one line. Alternative to that, you would have to say, for the function 1 over x, the derivative is negative 1 over x squared. More lines, more writing, more talking. Still, perfectly valid and 100. Cool? Yeah. Do you have to know this calculation for next class? The answer is yes. That's your 2.3 homework. I just put a new label on it, right? I just called it the derivative. That's all I did today. Now, if you are to observe this question in 2.3 problem 46, they're having the same question as A is 5. So you get to do the same thing, except each one of these x's is 5. So this problem has 4.6, has a 5 over there and 5 over there. The rest is the same. That's your 2.3 homework assignment 46. So try it now that you have, all of these steps.
How would you say the wording of the problem test?
Well, the wording would just say find the limit, right? I'm not going to say find the derivative. That's the difference, right? Because you know that, find the limit, you say, oh, I just have to solve the limit. Where in chapter 3 on exam, I would say find the derivative using the limit, right? Because we are going to have far cooler ways to find derivatives rather than, right? That will be up to you. Okay, so, well, this is it for this lecture. I'll explain more of the stuff later as we progress through the home. Bye.